Hey everybody! So when we last left off we were talking about the magnetic force on a charged particle, which is just F equals QV cross B. But if you break it down and look at the units, I know that force is in newtons, charges in coulombs, velocities in meters per second, and magnetic field is in Tesla. But a lot of times you're not going to just experience a charged particle going through a magnetic field. Unless you work in some sort of nuclear or particle physics lab. Instead, a lot of what we see in terms of electricity comes in the form of wires. So magnetic field actually has an effect on current carrying wires as well. And it all starts from this. So if I take these units and rearrange them a little bit, since I'm multiplying a coulomb by a meter per second, I can rearrange that as coulombs per second times meter, all crossed with the magnetic field. Whoops. Sorry, that should be Tesla, not just B. If I'm going to change things to unit, I might as well stick with it all the way through. So I have a Newton of force equals a coulomb of charge per second times a meter, all crossed with a Tesla of magnetic field. What this tells me, if you remember the definition of current, it's just charge per time. I can also find the force on a current-carrying wire as just the current times, well, meter, that's the unit for length, some sort of length, and Tesla's the unit for magnetic field. And this actually is the equation for the magnetic force on a current-carrying wire. You've got electric current, which in conventional current is just some positively charged particles all moving down a wire, all traveling in some direction. And if I know the length of my wire, as well as the strength of the magnetic field it's going through, I can find the force on that wire. And that's actually how the relationship between magnetism and electricity was first discovered. Again, the force is just IL cross B, well, ILB, which means the magnitude of it will just be ILB sine theta, where theta is the angle between the direction the current is traveling and the direction of the magnetic field. And then I'll use the exact same right-hand rule, karate chop in the direction of the current, point my palm in the direction of the magnetic field, and my thumb will give me the direction of the force. Nice. So, that's not too bad. Now here's the tricky part of this unit. So wires are affected by magnetic fields, but wires also produce their own magnetic fields. All right. So this is the magnetic field produced by a straight wire. You've got B, that's the magnetic field strength, equals mu naught times I all over 2 pi r. Now mu naught is 4 times pi times 10 to the negative 7 Tesla meters per ampere. That's just a new constant. It's called the permeability of free space. But we've got B, the magnetic field in Tesla. We've got I, which is the current in amperes. And we've got R, the distance away from the wire that you want to measure the magnetic field that's being created. And of course, good old mu naught, 4 pi times 10 to the negative 7 Tesla meters per ampere. Now, the reason that we're dividing by 2 pi r and not just r, the distance from the wire that I want to measure the magnetic field, is that the magnetic field actually forms a complete loop around the straight wire that's creating it. So, if I've got a straight wire, it produces a circle of a magnetic field around it. So the reason it's 2 pi r is basically it's taking the circumference of this little circle into account. The way to figure out the direction that the magnetic field is circling around this straight wire is through what's called the second right-hand rule. Basically, you just take your thumb, point it in the direction that the current is traveling, and then begin to curl your fingers around. The direction that they start curling is the direction that the magnetic field is circling around it. Now, of course, it's not going to be perfect because I can't curl my fingers in a full circle around my thumb. That is humanly, physically impossible. But it can at least get me started, and I can map out the rest of the direction that way. Now, wires don't only exist in a straight form. Sometimes they exist in what's called a solenoid. Now, a solenoid is just a series of loops of wire. Loop after loop after loop, building on itself. So I end up with a loop set of wire with some length L, a certain number of loops, which I'll just call N, and what I ultimately get, of course, and some current going through it, which will just be I. And what I actually end up getting is a magnetic field that closely resembles that of a bar magnet. In fact, you end up with one side being the North Pole, one side being the South Pole, where you have magnetic field lines that exit the north, loop around the solenoid, and go back in the South Pole, just like with a bar magnet. The really curious thing, though, is that these magnetic field lines are continuous, and in the middle of a solenoid, the magnetic field lines are perfectly straight. And then when they get to the outside, they loop around. So, why do we care about this? Well, a few reasons. It's the only way that electromagnets can work. You get a solenoid, wrap it around some sort of ferromagnet that's not a permanent magnet by itself, and turn on the current. It's as if you slapped a bar magnet right on that ferromagnet, and it is acting like a temporary magnet. Two, MRI machines. Those are kind of important. Basically, you put a human being inside a giant solenoid and turn it into a bar magnet and let it work its wonders. Now, to find the strength of the magnetic field inside the ideal solenoid, you end up with this, where B equals mu naught, where mu naught is still the exact same constant, that 4 pi times 10 to the negative 7. N is the number of loops, so how many times is this coil wrapped around itself? I is the current running through it, that'll be measured in amperes, and L is the total length inside the loops. Now here's what I mean by L. L is just going to be where the loops begin to where the loops end. It's not going to be the total length of wire that it takes to wrap that up. That's an important distinction. Now, to figure out the direction of this field, you just use what's called the third right-hand rule. This time, I've got current moving in a circle, so I can wrap my fingers around that circle, and the direction my thumb is pointing is the direction that the field lines inside of here, inside this solenoid, are going to be pointing. So, with a circular loop, I get a straight magnetic field through the middle, and then it loops back just like a bar magnet on the outside of the solenoid. So the deal with the second and third right-hand rules are that they're really, really, really similar. Basically, all you've got are two things to worry about. You've got magnetic field, and you've got current. One will always be a circle, one will be a straight line. So, a straight wire produces a magnetic field that circles around it. So in that case, the straight wire, my thumb will just be in the direction of the current, and the curl of my fingers will tell me which direction the magnetic field is rotating around it. Versus a solenoid, I've got a loop of wire with the current going in a circle, and it produces a magnetic field in the middle that's a straight line. So, the third right-hand rule is very, very similar. Whatever's going in a circle, be it current or magnetic field, gets the curl of your fingers. Whatever's going in a straight line, be it current or magnetic field, gets your thumb. Now there's one last little bit as well. You know that a changing electric field produces a magnetic field. That's what's happening with these examples of wires creating these magnetic fields around them. Not only that, a changing magnetic field also produces an electric field. So if all I do is take a magnet and move it through a coil of a wire, this is actually going to produce a current, and that'll produce a voltage as well. So to find this induced voltage, you need to know a little bit about magnetic flux. So if I have a coil of wire, and it's got some sort of cross-sectional area, call that A, so it's got some radius, and the area is just going to be pi r squared, then I can find the magnetic flux as the strength of the magnetic field times the cross-sectional area times the cosine of the angle perpendicular to the surface that the field lines are passing through. So when the field lines are passing directly through the center of that circle, I'll call theta 0, and the cosine of 0 is 1. So that's not too bad. Any other angle that the field lines will pass through, I'll get some strange angle theta. For a lot of these problems, I'm just going to have theta be 0 degrees. Which leads me to Faraday's law, which is actually one of Maxwell's equations. Now, Faraday's law looks super complicated, isn't as scary as it actually looks. So, I have the EMF. This is basically the voltage produced. That's the symbol epsilon there. N is going to be the number of loops in the coil. So this works really well when you've got a solenoid that a bar magnet is passing through. Now this delta phi sub b is the change in magnetic flux. The important word there being change. We're going to talk about how power is actually generated at power plants and whatnot. The trick is it has to be a change. I can't just hold up a permanent magnet next to a coil of wire and get electricity out of it. If I could, then all of our world's energy problems would be solved like that. Instead, I've got to have some sort of relative motion. So either I've got to be moving the magnet, spinning the magnet, or moving the coil or spinning the coil to get a change in magnetic flux. And delta T is the amount of time it took the magnetic flux to change. So if I move the magnet slowly, I'm only going to get a small amount of voltage versus if I move it really, really quickly. And that's the challenge of power production. And that's it. So the problems will often ask you what sort of voltage will be produced. You just need to know the number of loops of the coil, the strength of the magnetic field, or the change in strength of the magnetic field, the cross-sectional area of this loop, and the amount of time it took to change. So that was a lot of info in just a few short minutes. So overall, a changing magnetic field makes an electric field, and so that's why a charged particle moving feels a force, and a current-carrying wire feels a force when it's affected by an external magnetic field. At the same time, a changing electric field, which can be produced by a current, that's going to create a magnetic field. If you want to learn a bit more about this, look up Maxwell's equations. We're going to talk about it when we get to light, because it's just an electric and magnetic field propagating. But you can glance ahead if you want to. So to break it down, let's say I've got an existing magnetic field, basically a wire that's producing a magnetic field. Its own magnetic field will not affect it, but it can be affected by other outside magnetic fields. So the force on a charged particle in a magnetic field, F equals QV cross B, where B is the field that already exists and it's just acting on this charged particle. The force on a current-carrying wire in a magnetic field, F equals IL cross B, where again, B is a magnetic field that already exists from somewhere else, and it's exerting a force on that wire. And I can generate a voltage by a changing magnetic field from somewhere else. Epsilon, that produced voltage, equals negative N times the change in magnetic flux over the change in time. So that's if I already have a magnetic field, how other things are affected by it. Now, how wires produce magnetic fields that can then go on and affect other things. If it's a long straight wire, B equals mu naught I over 2 pi r. And if it's a solenoid, B equals mu naught Ni over L. Whew. So this is what we'll be doing this week. See you then.